understand localization for nonlinear Schroedinger equations. Results and puzzles. Okay.
Well, I would like to thank the organizers for inviting me to this meeting and for inviting me to give this talk. Now, this is work in collaboration with my student Evgeny Krivolapov that is in the audience here, and with Avi Sofer that most of you know. And there was a talk that was given on this a month ago by Evgeny, and Jan Fyodorov called me and asked me, give another talk and give a lot of technical details. So this is what I will do. So there will be a lot of technical details in this talk, and but I will try, but since some of you did not attend the first talk, and I know there is also a tendency to forget what is in talks, so I will remind you what is the motivation for that. So that's how it works. So our purpose is to study the nonlinear Schroedinger equation, where this is the usual Schroedinger equation, and we add here the nonlinear term. There are two versions. There is the lattice version, where these are points of the lattice, and psi is the wave function. There is the continuum version, and if the potential V is random, we have the Anderson model. Now we will study now only the lattice version, and we will study a situation that it is given by this formula. It means it is strictly one-dimensional. And although in many aspects it may not be important, however, it's extremely important to do the technical calculations. Okay, now the question is, we know that for beta equals 0, there is localization. That is, even all mathematicians agree to it for this case. And we ask, what happens if we switch on the nonlinear term? Does localization survive the nonlinearity? And many people think that they know what is the answer. Well, on the rigorous level, the answer is not completely known, but on the heuristic level, there are many people think what is the answer. The only problem is that they have conflicting answers. So here are the different views. I'm sorry that I will not mention the various names that are behind this conjecture, because some of them are given by many people. So the first argument, that is the most naive one, is the following. That it survives. Why? Assume it does not survive. So you have spreading. Then the nonlinear term decreases. Then we are back in the linear situation, and Anderson localization survives. Then there is an argument saying, no, it does not. And we have to do it a little more carefully. So assume that we have a wave packet of the width of delta n. The relevant energy spacing will be 1 over delta n. Now, the nonlinear term, that is the perturbation, is beta psi square, that is beta over delta n. And then all depends on beta, if it survives or not. And there is a critical beta. Then some people say, well, there is no critical beta. There is no critical beta. Immediately when you switch on beta, you kill Anderson localization. Then there is an answer, no, but it depends on realizations. In one realization, it survives. In another realization, it does not. And only this is supported by numerical experiments. Then there is a question, there is a statement, well, there is rigorous work, say, adding a localized time-dependent perturbation to mimic the term, and showing that even if it's periodic or even quasi-periodic, it does not. You get still point spectrum. Well, it's like this. Well, this is intuitive. This is supported by numerics. This is supported by other numerics. and this is supported by still other numerics, and all the numerics do not agree. And they don't agree. I will show the numerics in a moment. They don't agree because something subtle. To have numerics, what you need to do is to have an idea where to stop the calculation, to have some scale to decide what is infinity in time. And no one knows what this scale is. So there is, these numerics are very seldom, and usually these numerics support the heuristics of the people that make the heuristic arguments. So that is in some way a phenomenon, and I will tell.
The heuristics of the people who make the numerical calculation.
Yes, right. No, sorry, I'm confused. I confused it, and thank you. Yeah. So this is, and the problem, we don't have something like a finite time argument. It will be like the finite size argument, and I will comment a little more about the numerics. And then,
but the last bit is rigorous. Right?
The rigorous statement is if you add a localized quasi-periodic perturbation, the spectrum remains point spectrum. Is it correct? Okay.
But this is a disordered situation, right?
It's a disordered
you
situation.
have to specify where you apply this quasi-periodic perturbation.
In one point. In the localized region. Pardon?
But what if that point happens to be in resonance with the perturbation?
Which point? It's still a localized state. Now, I will have at some state, in order to get to the technical details, I will have to be in some way brief in some of these parts. Then there is, then it looks that there is a rigorous work showing that it looks that that to much extent in time the wings stay bounded, and then there are arguments of people that do dynamical systems saying, well, the nonlinear Schroedinger equation is a chaotic dynamical system, then we have chaos and everything spreads in space. Yes? Yeah, well, why don't you correct it? Tell it in the way that it should be told.
It does not indicate that it is bounded.
Yeah, it does not indicate. It indicates that it is spreads, and on this, one can conjecture, you conjecture that it spreads at most logarithmically, contradicting the numerical calculations. You don't know if it contradicts the numerical. Okay. Okay.
Do you mean that nonlinear Schroedinger equation without random potential is how
Well, no, with the random potential. Without the random potential, it's an integrable system. It's, well, I don't know. It's not on the lattice. This one is not integrable, but it's probably not chaotic. But the continuum version of it is integrable, and actually a lot of the calculations started as a starting point, took this nonlinear equation and added the randomness as a perturbation, and this line didn't go far. It means it produced a lot of papers, but it did not produce any decisive results. Now, why are physicists interested in this problem? And this because of the two fields, nonlinear optics and Bose-Einstein condensates, were in this field it is known as the Gross-Pitayevsky equation.
So, your last transparency, you made this remark about, I want to come back to this one, that chaotic dynamical system.
Yes.
But presumably the Bose-Einstein condensation refers primarily to a fixed point. And are you saying that it doesn't have fixed points? Or?
Well, in what sense? It will be a fixed point in the renormalization.
Is there a fixed point solution
of the Gross-Pitayevsky equation with a random potential? I don't know. It means, I don't know. How do we know that? For a random potential.
I don't know how you could know that.
No, I don't know. There is also, the question is even more subtle. It is not completely clear that there are many random situations where the Gross-Pitayevsky equation may be a bad solution because you may get fragmentation of the condensate in different parts. So there are indications, there were calculations looking on it as a scattering problem. And there you get out from the Gross-Pitayevsky regime. Well, there are indications that this approach may run into problems. Unless the system is very simple, like a trap or a uniform situation. Okay, so optics. So one example is these are experiments that are done by a group at the Technion led by Moti Segev. And what is done here, you generate a photonic crystal, and then one situation is that it is ordered, that it means it's translationally invariant it is periodic in the planes, and it is invariant in the direction of the fibers. The propagation direction mimics time, and then basically you look what happens in the transverse direction. So if it's periodic, you get spreading. If it is, and now you can introduce randomness with other lasers. The difficult part in this experiment is to make it translationally invariant in the propagation direction and random in the transverse direction. And so this was basically the thesis of the student Tal Schwarz, and they actually succeeded to do it. And what you find here, the following picture. This is the periodic situation. Now, we as theorists would like to see what happens when we propagate with the propagation direction, and what basically, but the experimentalists have a different setup. Their setup, the propagation is fixed, and they can vary the randomness. So this is what they do. Pardon? It's linear. At the moment, it's linear. Now, however, you see, it is linear for this experiment. However, the material is nonlinear, and this is the way that they make the fibers. The fibers are written with light. So, and this is the advantage of this technique that allows, with the same sample, to prepare many realizations, approximately a realization per 5 minutes, because the 5 minutes is the relaxation time of the material. So what is found when you change the randomness here, so this is the pure situation, so you have ballistic spreading. Here you have basically the case of diffusion, and here you have localization. So this is ordered, weak randomness, strong randomness. And what is given here is the effective width, calculate from the inverse participation ratio. And the error bars are not errors in the experiment. They result from the fact that the dimensionless conductance here is approximately 1.3, and then you don't expect these errors to be small. Now, for this case, you can make it non-linear just by increasing the intensity of the signal, and you have it attractive. So you see, as you increase the intensity of the signal, it spreads less. Now, I have to warn you that this is not the asymptotic time regime. It is, the length is limited. So this is the two-dimensional version. There is a one-dimensional version that is grown on a surface, and then you send the beam into one of these, like the equivalent of the fibers, and then if it's ordered, you see spreading. If it is disordered, but it's weak disorder, this is the effect of diffusion. Here it's a diffusion regime, and this is basically a localized regime. And then, now these are Bose-Einstein condensate experiments that were done by the Asper group, and basically what you see here, that when you prepare it in a parabolic trap, in a harmonic trap, then you switch off the trap and you send it to a random potential, and basically you see that you get localization, and afterwards there was a numerical simulation that basically demonstrated it with the Gross-Pitayevsky equation. And the problem now, the only place where nonlinearity enters here is on the level of the preparation in the trap. And afterwards, you get localization, assuming this equation is linear. So it does not penetrate, none of this penetrates in a systematic way the long time or the nonlinear regime. And this is very difficult, and we don't know to tell today the experimentalists what to do to get into an interesting regime from their point of view. Okay, so now I'll tell you about some numerical simulations, and in what happens basically in the experimentally relevant regimes. So far, it looks as you get localization, and that made a big fraction or part of the community very happy, because the naive argument seemed to work. But now, so this is the simulation of the Asper experiment, and the theory agreed with experiment and agreed with everything being linear for a very long time. But now, there are other experiments that show different results. And the one line here, the black one, is for the linear equation. Then you run the nonlinear equation for a long time, and you see that they nearly agree. But if you run it for a longer time, you see that that the nonlinear system starts to spread. And here you see this is the same, but with weaker randomness, and you see a stronger spreading for the nonlinear case. Now, and what is plotted here is basically the second moment, and you see that it grows, and the exponent with which it grows is approximately a quarter. So it's a very small exponent. And then there are other simulations that show that it looks as if it's flat, then it jumps and starts to spread.
What is
X is the distance from the initial point where you start. So this is the distance in space from the initial point. So this is what you look at spreading. Now, if you look at the wave packets, the way they spread, you have the exponential tail always survives and remains an exponential, and in the center, you create a flat region. So this is characteristic of this. But now these simulations claim that for a very long time, you don't see anything, and then you see a jump, and you see the jump only in a part of the realization. The time where you see the jump is very long, and there is no good physical argument for that time. And that what makes life more complicated. And the problem now, just to comment the way the simulations are done, the simulations are done with what's called the split step method, that you split the integration into parts. There are some intervals where you leave only kinetic energy. There are other intervals that you have only potential energies, and you integrate it this way. And what you are supposed to do is actually taking the limit for the intervals going to 0. now most of the now to do very long simulations, you don't make this interval too small, and what they do is they make these intervals of a certain size, then they reduce them by a factor of 2. They say, well, the qualitative picture does not change, and then in some way, then they change it again by a factor of 2. But usually, what you cannot do is to run for such times is for each realization to see that the result of the calculation is independent on the size of the interval. So therefore, what we wanted to do is to study it in some analytic way and get even some rigorous results. So for this purpose, what we do is we take this nonlinear Schroedinger equation and basically what so this transparency basically introduces the notation. This is the linear part. The eigenfunctions of the linear part, we call them un. We expand the wave function in terms of these functions, where m is here the index of the state and n is the latticide. And these are the expansion coefficients, and would the equation be linear, these expansion coefficients are constants, and now they are not constants, and we will calculate them in perturbation theory in beta. And we'll see how far we can go and how much of the details I will be able to present. Okay, so this is and um will always be a state that is localized near m. And now it's an important issue of indexing of these states for making rigorous statement. So the states are indexed by their center of localization. It has to be decided in some way, for example, around where the mass of this wave function is the largest. The crucial point that can be shown rigorously that allows this is that you cannot have the density in a fixed of such states in any fixed box is basically bounded. Otherwise, you could not do it. So from physics point of view, it's trivial. Mathematics point of view, one has to show it. But this is a known result, I think. But we checked it independently. And now, then you get equations for these coefficients where this is shows us that this is the nonlinear contribution, and this is basically the overlap integral of the wave functions. So it's an overlap integral of 4 wave functions, and it is basically negligible out of a range xi that is the localization length. So these points have to be within the localization length in order to have a big effect. And this is one thing that allows to drive this theory. Then we introduce a perturbation expansion of the coefficients C in terms of these betas, and we calculate order by order this theory, starting from a state, an Anderson state localized at 0. And so this is the strategy, and we'll see how far we can go. Then I will show you the first step in this strategy. So you write the equation for C1, that is the first order correction, and you get this differential equation that is trivial. For n not equal 0, you just integrate it and you get an answer. Then you will use it for the next step and so on. Now, for nonlinear systems, there is an addition. A problem does not exist for linear systems. That for 0, for example, here, and in the later order it will exist, show up in all the other cases, you find that this does not oscillate. So this is, if I will integrate it, I will see something that goes linearly in time. It's a problem that is known for nonlinear systems. The solution is known since the time of Poincaré, and this is to introduce terms in a way to remove this. So, and this is known as the removal of secular terms. So I will have replaced the original energies by new energies. And for example, here I will have to add to it the V000, and then I get rid of all these terms. And now we can show that for this problem, one can do it systematically in all orders of perturbation theory. So then we write the energy as an expansion of these are the energies of the Anderson model, and these are corrected energies. And we call this the renormalization of energies. Then what we change the ansatz and use these new energies. And then we encounter, the next problem that we encounter are small denominators. These denominators can become small. So if there are two, there are a lot of results that are known, but there are sometimes combinations of more energies. Now, we will treat it in an approach that was developed by Eisenman and Molchanov, and basically raising it to a power that is smaller than 1, and averaging and getting results from that, and I will show how one is doing it. Okay, now from the leading order, the result that we can obtain at the moment rigorously to I think to the satisfaction of all mathematicians is that for a time that is shorter than 1 over beta squared, and there is a constant here that, well, it may be complicated, exponential localization is preserved. So at a distance that is larger than the localization length of the Anderson model, the probability of finding this particle is exponentially small with the same localization length as of the ordinary model. So this is what I'm going to show you. Then I may, if there will be time, I will make some other comments. But because there are a lot of interesting technical details in this. So this is basically the strategy. The strategy is to start with the initial wave function that is localized at the origin, at the state, it's an Anderson state that localizes the origin, then to write an equation for the rest, for the remainder, and then to take care of this equation. So the first thing is to take the small denominators, average them, then you're not interested in the average, you are interested in the probability of what will happen. From the average, using the Chebyshev inequality, you can get a probabilistic estimate of what's going on. And all the results will be probabilistic. Then you can use something that's called in this language a bootstrap argument, that from the growth to show that this term cannot be destroyed too fast in time. And this will basically be, so now I will go through this, and I will not go through all the details, but I will try to give the flavor. So this is the program. And now we start with step 1, an equation for the remainder term. Okay. So again, we have the Schroedinger equation, and what we want is to find, to show that with some number A, that will be nearly the localization length, basically the CNs are bounded, because the CNs are the expansion of the coefficients of the Anderson states. And what for this we have basically show that the following ansatz holds for the remainder, that is the correction to our initial state. So we will write the Cn, the expansion coefficients, in the following way: the delta at the origin plus a remainder. And we will now write an equation for the remainder. Okay. So this is the messy part, and I don't, well, one doesn't have to follow everything here, but one has to see, first of all, that one can do it. Second, that what are the various terms, and you see there are nonlinear terms, there are linear terms in the remainder, and they go with decreasing powers in beta, and that's the entire equation for this remainder. And now the next step will be to analyze the linear equation of the remainder, and the other terms are already of order beta squared. So the other terms I will just bound. I will not bother to integrate them very carefully. Okay? So now here is basically the equation for the linear term after I removed one secular term that I don't want to have. So and what you see here, it's a linear equation given in terms of the remainder terms of other components. So it's the remainder at the end component as a function of the other components. And what's crucial in this equation, you see you have also the complex conjugate everywhere following. And the next step is basically now to integrate and to write it as two parts. And you see I don't want to go to all the parts, so I will just focus on one of them and bound it. The second one, it's exactly the same game. Now, so we have to do this integral. Now I have to get results up to order beta squared because I want to make a statement of t times beta squared. So that is not good enough just to bound. So we have to do another step. And the other step is integration by parts. And when one integrates by, so one takes this term, one takes the indefinite integral of something that we know specifically, and the derivative of the second part. But the derivative of the c we know from the equation, and then by substituting it, we get everything now to order beta squared, and this is to the order beta. On this one, we know we'll do the integral again because there is nothing mysterious. There is no c here. So you see, we get such expressions, and you see our first problem are the small denominators that are full, and there is no theory actually telling us how it's a combination of several energies, so we have to see how we treat the combination of several energies. So here there are various small denominator terms, and you see there are many of them. So the strategy to treat them will be the following. The v's are not very bad terms. The v's fall off very fast. So, and we can actually bound them. So when we average, we can take them out from the sums and use, no, not from the sums. We can, from the averages, we can bound them over all realizations. Nearly all the realizations. We have to throw out some realizations. And you can realize that we cannot do better than throwing out some realizations because there are realizations that are nearly periodic. They have a small vanishing measure, but they are around. And then averaging the denominator. So now we will go to the step of the small denominators. Okay, so now a specific problem that we have is to average such a denominator where the function f is some combination. Let me see if I find, okay. The f, okay, let me tell you what is the function f. F is some combination I, Ci, EI, where EI are the eigenenergies of the linear equation of the Anderson model. Now these combinations can be very small. So now we want to average where the epsilon i's are the diagonal matrix elements of the Anderson model. And I will assume that everything is in a box of the size lambda. And then I will take the size of the box to infinity. Now we have to do an integral over these epsilons. with a function f. So that looks something very bad because we don't have control on this denominator. So we change variables to this new, basically we'll change. Okay, so I want to change to new variables, throwing out one of the epsilons that I will tell you later. We'll use an optimal epsilon and replacing it by the function f. That is that sum that is written there. Now, what may happen is the function f, it's a complicated now domain, or it's a huge domain in the epsilon space that is the size of your box. So that's huge. Now the function f on that domain may oscillate. We may have multiplicity of different regions where it is different. So we have to split it into domains where f has the same sign. So this is what was done here. Now, and now f can be now the f itself is not a problem. It can be easily bounded because it's a band, the energies are bounded. There's no problem. We bound f by q. The problem is with the Jacobian of this transformation that you have to bound, and it appears in the denominator, so you have to bound it from below. So to find lower bounds is usually difficult. So what I'm doing here is that, so I will assume for a moment that we found such a bound. And if we found such a bound, and there is a global bound, we factor it out, and then we integrate over all the small domains where the function, there are many of them, where the function has the same sign, but they become very small. So when you integrate over all of them, and sum over them, the integral is basically a finite number of order, basically of order of 1 over the size of the region where the Anderson epsilons change. So it's the width of where the Anderson and delta is the width where the Anderson energies change. So then we have a bound if C delta, the lower bound on the Jacobian, is a finite number, I basically get a bound on all these small denominators. So now I have to convince you that you have such a bound. So to have such a bound, you have to know how the eigenstates look asymptotically. Now, physics-wise, we know that they will fall off exponentially. Now, mathematics-wise, it is not obvious. Now, for the one-dimensional Anderson model, it can be basically deduced. Okay, so for the one-dimensional Anderson model, you can get it basically using the proof of localization that was done by De Leon, Souliard, and Levy, and combined with the Furstenberg theorem. Now, the point only is, and this I don't want, that it doesn't say that the wave function completely at all the points will go exponentially, but at least at every second point, and some people now claim that this is probably not correct, but if I have time, I will show it. Now, I want to remind you that that is correct only for the strictly one-dimensional. For the strip of 2, I don't see how one shows it rigorously. Okay, so then how to relate it to this function f, with the derivative of the function f with some epsilon. Now what we have to, technically, it has to be a derivative with respect to a sum of 2 epsilons that are nearest neighbors. So now we take these energies and we differentiate them with respect to these epsilons, and using the Feynman-Hellman theorem, you get that this is the combination of the eigenfunctions squared. And this decays. So then what you have to do, and I will not go and do all the details, then these states, there are a few possibilities. That either these states that are involved in this sum are very close one to the other, they form a cluster. Then you take the point with respect to which you differentiate outside of this cluster very far, and then there is one that dominates. There is one that dominates that has the longest localization length, because the localization length depends on energy. Now, if they sit on different clusters that are very far, if they sit on clusters that are very far in space, then you choose one of you choose to be the Cj to be outside one of the clusters, and outside one of the clusters, and far from the others. The crucial point is for this that there should be a value from where on, at least at every second point, it falls off exponentially. And not just being bound by an exponential. So now, then comes the issue. There are boundaries of this between these domains. How large are the regions where two energies can be very close, having exactly very close values of the Lyapunov exponent? Well, so for this, you have to estimate these regions and then there is an estimate of finding two energies in an interval and by the same interval by Minami, and fortunately the estimate works so that the probability of being in an interval of the size I goes like the square of the interval, but it has the size of the system. So if you take this interval to be smaller, like 1 over the size of the system squared, you basically find a probability that will go to 0 when the size of the system goes to infinity. Now, to some extent, you see the probability of levels becoming very close is very small. Now, it will be bad to put as the size of the system the whole box, but I will put it just a box that closes the cluster, that covers the cluster that I'm interested in. So after doing that, basically now there is another point, there is another technical point. Since I don't use the energies themselves, I have to shift them by this renormalization procedure. I have to do something else, but this is just a technical point. And now I have to see how you bound the integrals. So now I bring to the rescue the fact that the overlap integrals are exponentially bounded, and we know the bound. And now here you have, here you have the part that there is there may be a deviation from strict exponential behavior, and there may be dependence on the center of localization. All this is taken by this factor that is not well known to all mathematicians. And then what you go further, and now we have to bound a term of this form. So what you do is basically now, so we will bound this quantity to the power s, and then use different, and s is between 0 and 1. And then what happens is you have this to the power s, and then you factor out all this stuff. You just bound it, and you use the average over this quantity that we calculated, and it's finite. And in the end, you end up finding that this is bounded roughly by the localization length, but for technical reasons of rigor, you have to subtract here an epsilon that exists, that takes care of all the deviations from exponentiality. And then the next step, so we are here, and now we have to produce a probabilistic bound. Okay, so this is a technical detail for some of the terms. You have two of them, then you have to make S smaller than a half, and then you use the Chebyshev inequality, and basically this is basically the statement of the Chebyshev inequality, and then what you just substitute here the average, and then then you raise everything inside by the power S, and then you choose the free parameter B that is still at your disposal, and you get in the end that the probability of all these terms that are involved in the game is smaller than a constant times something that depends on eta to the S. Now eta is something that you have the freedom to choose, but you cannot make it larger than the inverse localization length. So then you can play with this, and so you show that the probability, if you are very far, the probability to violate this bound is exponentially small. Then, after having this, so you have small terms, and now I'm coming back to what we want to bound. So here we have the linear term that I was talking about. Then there are the other two terms that you'll just bound the integral 1 minute. Okay, so then what you do, you get basically then. So basically then you get this constant m that is, well, I told you that I want to bound Cn of R by some number m to an exponential gamma minus epsilon x. So this is the equation for this m. And now this m, you want it to stay bounded for some time. So you substitute all these guys, and then now this is now the bootstrap argument. So what you do is you get a bound on this m of this form. Then you say, okay, let's ask, can this become larger than something? Say, so g is a constant, say, to become 2g. And what you can show that it cannot happen as long as b squared times t is small. And these are, the important thing is to show that these are finite constants, and this is what we did. So the conclusion here is basically that there is a time t0 that is of the order of 1 over beta squared. There is a constant here that for smaller times, everything will remain exponentially bounded. Now, then, so this is the summary of what we did, but since it has puzzles in it, so these are the questions that are left. What is the long time asymptotic behavior? This is not a question that's not settled. How can one understand the numerical results? Even they are not asymptotic, it's interesting. It means the second moment goes with a certain power. So first of all, is it something real, or it's a problem of the numerical scheme, or there's something else? And then now what is the time scale that is relevant for the long time asymptotics? So this is something crucial to check the numerical calculations, if they are at all relevant, or they are just a result of some artifacts. And now, if we understand this, the question is, when is this time scale short? And then we can tell the experimentalists what is a good time scale to look for these effects. So this is what is left. I'm sorry I couldn't go to all the details, but I'm around here for in the afternoon. I'm happy that to hear comments, and I will in particular be happy to hear from the rigorous mathematicians what do they think was done not completely rigorous here. And so we always like to hear such things, because the part of b of 1 over t squared is supposed to be, I think, is rigorous. So it means, so if there are few things in the puzzle still to close. So, but this should be a rigorous result. So thank you very much.
Yeah, first of all, not a rigorous mathematician, but on the opposite wing of this conference, but still have a question. For this problem, is it so? What is known in? So you started from sort of the localized situation, and then showed that it remains until some time. So are there some results when you start sort of from the opposite case, from the metallic case? So what is the effect of nonlinearity? So we understand well what are effects of interactions in the problem with electron-electron interaction, and there is some similarity. So the question, and there we can control the talks here by Gon and Gershon's on what are effects of interactions. So are there some analogous statements?
Okay, so the question that if I understand correctly, is what is known about, first of all, about the nonlinear problem. So the nonlinear problem, if there is no randomness, so if you are not on a lattice, that is a case that is known to be integrable. So it has the infinite number of constants of motion. Now for basically for repulsive nonlinearity, asymptotically everything will spread. For attractive nonlinearity, you get solitons if you are in the continuum. And these are stable, and also the shape of the solitons is known. So this is something that is textbook known. Now, if you are on the lattice, there is less known. There is just for a specific type of the structure of the equation. This is not the one that I used. There are solitons. This is not an integrable system. However, numerically, with the traction here is something tricky, because it depends where you are in the band. So if you are in the center of the band, it behaves normally. If you are close to the edges of the band, it is what's called something anomalous. So they behave as particles with a negative mass. If you start something concentrated, so the particle is moving in the opposite direction to the gradient of the potential. And now since you have nonlinearity, you mix between them. So the sign on the lattice is not that important for if you look at this problem. Now, if you add a little bit of randomness,
I think I asked more. Imagine you have some randomness, but still it's an delocalized regime without, and then you add nonlinearity to this problem.
Okay, so you have randomness. So the randomness is weak. It's one dimension, so you cannot be in a delocalized regime.
Yeah, okay, but you can also consider this in
yes,
calculus.
I can consider it, and then you add nonlinearities. If it's, I really it's very hard to guess something on the basis of analysis, but I can spread guesses on the basis of so I think if it will be repulsive, so it will spread or something like that. But this is something obvious. It's not based on any analysis. This is now the other question is how to relate this to a problem of interactions. So the only place where I know how to do it, one is not that I know how to. It's done. It's the Gross-Pitayevsky case that you put delta interactions and then you do this calculation that they did. Any other thing that you still would like to know more about it? So, because
there are many things, but probably
okay.
Other people should be.
Actually, I can try to ask my version of that question,
yes.
but somehow focus it on more, macroscopic properties rather than details of integrability or not.
Yeah.
So if the expectation here that there are two possibilities. Either the system remains localized in the narrow sense, or maybe in the broader sense, and so the diffusion constant remains zero, or the system delocalizes and there's a finite diffusion constant.
Yes.
Right. Okay. So now, if
there are other variants. The other variant is that to reconcile it with the numerics, with the growth of the second moment, it may be power localization. But the numerical experiments that observed this growth, this strange growth of the second moment, didn't observe power law tails. So, okay.
Let's stick with two possibilities. So the question that I want to ask, I think in line with the previous question, is if I start in the regime of weak disorder, is there one place that at least numerically, say, if I take this model on the lattice where it's non-integrable, can one actually see diffusion? I mean, is there a metallic phase in this model at weak disorder that you can demonstrate?
So first of all, since it's strictly one-dimensional, without the nonlinearity.
No, with nonlinear. I want you to take a nonlinear model on the lattice.
Yes.
And
there is a case where no one has seen something like diffusion. Something that only this anomalous type of diffusion, and so this is the way that I understand it. Maybe, but people might. Well, I don't think anyone looked carefully enough. I don't think that. I don't think that anyone observed the regime with linear growth of the second moment. Well, okay.
I just wanted to comment that that one thing one can do, and it has been done, I believe, in the math literature some time ago, is if you take a potential and you take a focusing nonlinear Schrodinger in 1D.
Okay.
Okay. Then you will get a lot of bound states corresponding to essentially every well in the semi-classical limit. Every well will be trapped, and there's no assumption about. I think this would work even for a periodic array of wells. Mm-hmm. And this is work by Weinstein and Floor many years ago. So what they do is a little different from the strategy, and I think it's a very interesting strategy. You're perturbing off the linear thing. They perturb off the nonlinear. In other words, they know the system's integrable. They know what the solitons and so forth look like, and they use that to.
And what was the result?
That you get these localized states in the wells.
You get localized states in the wells, even for the periodic case, you don't get extended states.
But it's focusing.
Good.
Focusing.
It's a focusing, because we didn't see.
So they have some So they get some nonlinear eigenstates. I should be careful. They prove the existence of some nonlinear.
Okay, this is a different. Okay, if you are interested in nonlinear eigenstates, I might have to mention there is work by Albanese and Froelich for the lattice version, and what they find is that there is a rigorous proof that the stationary states, so it means these are the states of the eigenstates of the nonlinear Schroedinger equation, they are exponentially localized, and then we succeeded with Alexander Yomin and Kiron Malik to show in a non-rigorous way that the localization length is identical to the one of the nonlinear problem, but we did it in the continuum, and it's not rigorous. What the non-rigorous step that we did is the same step that physicists do between the Alaba-Hollande argument and the proof of the De Leon, Souillard, and Levy that you can do the matching in the center.
So the dependence of the time scale on which you control the situation, the dependence on the strength of the nonlinearity. But what is the dependence on the strength of the disorder?
On the strength of disorder, it is buried somewhere. I did not really, the time, the situation will improve as the disorder becomes stronger. I didn't go, I don't remember the moment the exact constant. It means, but one can get it out. It's buried, however, it's buried in a lot of constants on the bound on this wave function. So I'm not sure that it's so easy to decode it, but it's decodable. So thank you. We'll decode it and some time I'll answer it.
I think we should stop here, but I would like to make one more announcement. We were told that David Towers has put his notes of the talk he gave, the first talk at this conference, on his website, and this is accessible via the website of the Institute from the abstract of the talk. So we reconvene now. Let's first of all thank both speakers.